Alright, we're going to continue with the next part of the thermochemistry lecture. So let's just kind of do a reminder on systems. So remember, a system is anything in a process that is being observed. It's what you're paying attention to. And everything else around it is called the surroundings. And together they make up everything, which is called the universe. Now, a system can literally be any physical thing. It can be a flask that a reaction takes place in. It could be the solution that's in a flask. It could be a box. It could be literally a house, right? It's whatever it is you're paying attention to when there is a change or a process. Now, it turns out that there are three kinds of systems. Or better yet, three types of systems. And they're actually defined by what can be exchanged between the system and its surroundings. The two things that we'll focus on are energy and matter. Remember, matter is anything that has mass and takes up space. And energy is the capacity to do work or produce heat. For example of these, let's say matter, literally look around you. Any physical object is a form of matter, even matter. And you don't necessarily have to see it. There's matter in the air, there's matter in liquid, solid, any one of those three states. Every physical thing around you that you see that has matter and mass, that has mass and volume is matter. Now, energy has many, many forms and is constantly converting. But the most common examples are mechanical energy, which includes kinetic and potential. There's also light, heat, electrical. But the main one that we're going to focus on is heat. However, any kind of energy qualifies here. Alright, so like I said, there are three types of thermodynamic systems. These systems are open, closed, and isolated. Alright, so now let's talk about what can be exchanged. Remember, our two options are matter and energy. An open system allows for the exchange of matter and energy. So if an open system allows the exchange of matter and energy between a system and its surroundings, there are several examples that we can use. We'll keep it very simple. So an example of an open system can be a baby. So for example, if the baby is our system, if that's what we're paying attention to, matter can go into the baby and leave the baby, right? So food is matter and that goes into the baby, and as the baby digests it, the baby can poop out the food or waste, and so matter can leave the baby. You can drink milk, you can breathe in air, all these ways for matter to enter the baby. He can breathe out air, he can throw up. These are ways that matter can leave the baby. So matter can enter the baby. But there's also an exchange in energy, because as the baby's body is working, as is experiencing homeostasis, which is the regulation of his body, heat is being produced, leaving the baby, but heat can also go into the baby by giving him a nice warm bath. He'll absorb the heat and get warmer. So that's an example of an open system. Matter and energy can be exchanged between the baby and the system. The baby is the system. Between the baby and its environment, right, or the system and its surroundings. Another example, an easy one to understand, is, for example, your house. So people can walk in and out of the house, so that's an example of matter entering and leaving the house. And energy can also enter the house and leave the house. On a sunny day, light energy can enter through the window. If it gets really hot, the heat can sort of pass through the walls of your house. Of course, heat can also leave your house. You can shine a light out the window and light can exit the house. So these are examples of matter and energy being able to leave this system. So it's an open system. Another example, a frying pan. You can put matter in it, you can put eggs, you can heat it up, it'll absorb the heat. Open system. In a closed system, you are not allowed to exchange matter. However, you can exchange energy between a system and its surroundings. So a rough example could be, say, a planet like Earth. And the reason I say rough example is because we're going to go ahead and do this. We're going to assume that, nothing leaves the Earth physically and nothing lands on the Earth. So we're not going to include meteors, or meteorites. We're not going to include space program stuff. We're just going to assume, and the reason we're going to ignore that is because basically the amount that leaves or enters the Earth is just so small it's considered negligible. So we can basically say that matter doesn't really enter or leave the Earth. That's in this case. However, light from the stars, including the sun, does hit the surface of the Earth, and it does reflect that light. So light is able to hit the Earth, it's able to enter the system, light is able to leave the Earth. So there's our example of energy being able to enter and leave the system. Also, when heat warms up, heat leaves or escapes the atmosphere as well. So here we're just looking at a system where energy is the only thing that can enter and leave the system, hence closed system. Another example of a closed system could be a glow stick. So a glow stick has some chemicals inside of it that when you bend the glow stick, it actually breaks a little glass tube that's inside of another solution, and when they mix, a chemical reaction takes place, and one of the products of that chemical reaction is glowing light, and the light is able to leave the clear plastic. However, the materials stay inside the glow stick. So that's an example of light being exchanged between the system and the surroundings, but not matter. Now, I do want to state something. A system can change the type of system that it is if this glow stick were to tear open and some of the solution were to leave. It would no longer be a closed system. It would be an open system because now you have an exchange of matter between the system and the surroundings. And the last type of system is called an isolated system, where matter nor energy can be exchanged between a system and its surroundings. So an example would be something like a thermos, or a Yeti, or even some ice chests. Now again, I have to be clear, right? Obviously you would think it's an open system because you can put things inside of it. But the idea is that once you've closed it, there is no food or liquid or any kind of matter allowed to be exchanged between what's inside this thermos and its surroundings. So it's intentionally, or it's ideally trying to work as an isolated system. We know this because we put a drink in there we put a drink in there and it's like super, super hot, and then hours later when you open it up and it's no longer an isolated system because it's exposed to the surroundings, the idea is that it's still the same temperature because energy was not able to leave your system. It would just stay inside the system. But as I said before, the moment you open it, you stop it from being one kind of system sometimes. So this stops being an isolated system when that lid comes off. But before that lid comes off, ideally it functions as an isolated system. And the reason I say ideally is because if you put a liquid inside of a Yeti or a thermos and you come back a day later, a week later, the temperature will not be the same as when you first put it in because it's not perfect, and energy can leave, but it's so slowly that you don't notice it for a long period of time. For a short period of time, but after a very long period of time, it can escape. All right, so those are the three kinds of systems that I want you to know. Now let's go into calorimetry, And if you know your Latin roots, calor tells you heat, metri tells you the measurement of. So our main focus is basically a specific type of energy, which is heat, and we want to study how certain systems gain or lose heat. And we also want to be able to measure these heat change in different kinds of experiments or chemical or physical processes. Actually, now that I think about it, before we actually go into calorimetry, we should probably learn two more topics. Well, one more topic. It doesn't matter what I say. We got to learn about what's called specific heat capacity and heat capacity and joules and calories. So let me actually go back to the first. Alright, just corrected it. So we're not doing calorimetry, we're doing specific heat. Alright, so you've probably heard of, someone saying that they want to work out because they want to burn calories. What does it actually mean to burn calories? Well, it turns out that as you exercise, your body generates heat. And this heat is measured in units, which are called calories. So as the sugars and fats are broken down in your body and converted into carbon dioxide and water, it generates heat. Now, although there's not an actual fire burning the sugars and fats within your body, chemical reactions, and we're talking thousands of chemical reactions that take place inside your body, basically accomplish the same result. If you were to burn sugars and fats, you would make carbon dioxide and water. Your body does the same thing, which is why you produce heat, because in an actual explosion or combustion reaction of sugar or fats, you get carbon dioxide and water and the same amount of energy being released. So let's start defining some of these technical terms. So a calorie is basically the amount of energy you need to increase the temperature of exactly 1 gram of pure water by 1 degree Celsius. So in order for 1 gram of water to go up 1 degree Celsius, you need to add heat. That amount of heat is equal to 1 calorie. So, to be clear, if you had 1 gram of water at 25 degrees Celsius and you wanted to increase its temperature to 26 degrees Celsius, you would need 1 calorie. If you had water at 30 degrees Celsius and you wanted to increase its temperature at 1 gram of water by 1 degree Celsius, you would need 1 calorie. Now, it is important to note a difference and not confuse a calorie with a calorie. In the scientific community, often we use this calorie right here. However, just like there's calorie with a lowercase c, there's also calorie with an uppercase c. This calorie with an uppercase c is the one that refers to energy contained in food. So the uppercase C is your dietary calorie. So if you were to go look at any food product to see how many calories it quote-unquote has, which it doesn't, you'll notice that the word calorie is an uppercase C. Or if you look in other countries, you might not even see calorie. You might see kcal. Well, the reason that you would see kcal is because K stands for kilo, and 1 calorie with an uppercase C is equal to 1,000 calories with a lowercase c, and 1,000 can be replaced with the prefix K for kilo, 1 kilocalorie. So again, this is the one that we see in the food industry. So when you see something has, for example, 40 calories, well, it has 40,000 calories. Now don't go crazy and think, oh my God, I'm having so many calories. In this case, this actual scientific unit that we use in the world of science is actually so small that for the food industry to give their caloric information or dietary information, they have to use a bigger unit, because this energy right here, a single calorie with a lowercase c, is just so small. We need to use something, a unit that's a lot bigger to represent it. So let's be clear, if we have a statement that says 10 grams of sugar has 41 calories, what that means is those 10 grams of sugar, when they're broken down inside your body, they will actually release or produce 41 kilocalories of thermal energy or heat to produce carbon dioxide and water. Now, calorie is not even the star of the show. The star of the show is actually the SI unit for heat and energy, which is the joule. It was named after English physicist James Prescott Joule. A joule is slightly less than a fourth of a calorie. So if 1 gram of water had gained 1 joule of energy, its temperature would not go up 1 degree Celsius. It would go up about 0.239 degrees Celsius. But there's a relationship between joules and calories. It turns out that 1 joule is equal to 0.239 calories, or the more commonly known one that we see is 4.184 joules is equal to 1 calorie. In this class moving forward, we'll be using this expression more. Alright, so now let's talk about another term that sounds extremely similar. This term is heat capacity. Heat capacity is the amount of energy required to increase the temperature of a substance by 1 degree Celsius. Don't confuse it for calorie. Calorie was the amount of heat it takes to increase. Calorie is the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. Heat capacity is much more general. Heat capacity is, again, the amount of energy it takes to increase the temperature of a substance by 1 degree Celsius. What that means is that the heat capacity of an object or substance depends on the mass of the object, and it also depends on the chemical composition, what it's made out of. So you can think of it like this: the greater the mass of a substance, the greater the heat capacity it's going to have. For example, let's say we have 1 cup of water and we have 1 drop of water. Well, again, heat capacity is the amount of energy. How many joules is it going to take to increase the temperature of a cup of water by 1 degree Celsius? How many joules is it going to take to increase the droplet of water's temperature by 1 degree Celsius? Which one has a greater heat capacity, or which one requires more energy? Very good. The cup of water, not the droplet of water. The droplet of water will not require very much energy for its temperature to go up, but the cup of water is going to take some time. Now, in that example, both cases were the same substance, water. So besides varying with mass, the heat capacity of an object also depends on its chemical composition. It depends on what it's made out of. It follows different substances with the same mass. It follows that different substances with the same mass may have different heat capacities. So for example, let's say on a sunny day out on the street, there's a puddle of water, and next to the puddle of water, there's some little random piece of iron metal. And both of them have the same mass, 20 kilograms. So, would both of them have the same heat capacity? What that means is, if they both received the same amount of energy from the sun, let's say they were both out at the same time, and all the time that they were outside, they were getting the exact same amount of energy from the sun, would they both be the same temperature? Well, it turns out that if you were to go and touch the puddle of water, it might be rather cool, but if you were to touch the metal, it turns out that the metal might be actually too hot to even touch. Well, that means that the metal has a much lower heat capacity. What that means is it takes less energy to increase its temperature by 1 degree Celsius. Water has a much higher heat capacity, which means it takes a lot more energy to increase its temperature by 1 degree Celsius. So it's actually going to take us into our new term, which is specific heat capacity. And get ready for this definition. It's going to seem or sound extremely similar. The specific heat capacity is the amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. So let's take a look at a table. So this table has a list of different substances, and it has their specific heat capacity in joules per gram degree Celsius and calories per gram degree Celsius. Now this should look familiar because earlier we said that 4.184 joules was equal to 1 calorie. Of all the substances on Earth, water is the substance that has the greatest specific heat capacity. What that means is water requires the most amount of energy to increase a gram of its sample by 1 degree Celsius. Grain, ice, steam, they have lower specific heat capacities. Chloroform, even lower. If you look down toward the bottom, you might notice that we have a bunch of metals: iron, silver, mercury. Iron, silver, and mercury have very low specific heat capacities because it doesn't take much energy to increase their temperature. So let's say, for example, that we had 1 gram of mercury and we had 1 gram of water. So again, that's water, this is mercury. We have 1 gram of each. And let's say we take their temperature, and right now they are both at 25 degrees Celsius. And let's say that we add a certain amount of energy. I'm just going to pick that value there. Let's say that for the water we add 4.18 joules of energy. And also for the mercury we add 4.184 joules of energy. Because water's specific heat capacity is 4.18, what that means is 1 gram of water requires 4.18 joules of energy in order to go up 1 degree. So 1 gram of water will convert from 25 degrees Celsius to 26 degrees Celsius when it gains 4.18 joules. Now, if we look at this mercury example, also at the same initial temperature, if we add 4.18 joules to it, we have to look at specific heat capacity. Its specific heat capacity is 0.14. That means this is how much energy is needed to go up 1 degree Celsius, to have 1 gram of mercury go up by 1 degree Celsius. But we're adding way more. We're adding 4.18. So if we want to know how many degrees it goes up, we got to take that 4.18 joules and divide it and see how many times 0.14 goes into it, which comes out to 29.9. That's how many degrees up this mercury would go. So mercury would go from 25 degrees Celsius to 54.9 degrees Celsius, given the same amount of energy that 1 gram of water was given. Again, the difference is the specific heat capacity. This is why a puddle of water versus a piece of metal, the same amount of mass, the metal is going to be so much hotter because it takes less energy for its temperature to go up a single degree. So water having a very high specific heat capacity is extremely important, especially in nature. Just as it takes a lot of heat to raise the temperature of water, water also releases a lot of heat as it cools. So water in lakes or oceans absorb a lot of the heat from the air on hot days, but they release it back into the air on colder days or cool days. So for example, let's say we take a look at California. San Francisco's like right here, right on the Atlantic Ocean's coast. Actually, now that I think about it, it's not the Atlantic. We're the Atlantic. The other side of the United States is the Pacific. So San Francisco is located right on the Pacific coast. So the high specific heat capacity of the ocean helps keep the temperature in San Francisco much more moderate than towns and cities further inland. So on a given day, San Francisco may see a high of 78 degrees Celsius, Santa Barbara might have 80, LA 92, San Diego 74, and on the other side of the state, cities like Fresno, Death Valley, Palm Springs, they may be seeing temperatures like 109, 125, 119. Yeah, and I think I realized that I might have said degrees Celsius. I mean degrees Fahrenheit. So just by being on the coast, that water that absorbs a lot of the heat lowers or makes the temperatures much more moderate for cities nearby than cities that are much more inland. They don't have that water to absorb some of that heat, which is why they experience much hotter temperatures. Alright, now let's take a look at a little bit of math work. This right here is your equation for specific heat capacity. So I'm going to go ahead and label each of them and describe them as I label them. So this is your specific heat capacity, also known as specific heat, right? It's the amount of energy, usually joules or calories, required to increase the temperature of 1 gram of a substance by 1 degree Celsius. So these are the units for specific heat capacity. Now, if we look at the other side of the equation, we have Q. If you remember from a previous lecture, Q represents heat. It is the heat absorbed by a substance for its temperature to go up. And that unit is typically joules or calories. It could be kilocalories, any unit of energy. But those are the most common ones. M obviously is going to be the mass of a substance. And for specific heat capacity, it must be in grams. Times, then we have this triangle. So this triangle T means change in. So delta T means change in temperature. What that means is the final temperature minus the initial temperature. So once we know those two values, we can calculate the change in temperature. And lo and behold, temperature is going to be in degrees Celsius. So you've got joules over grams times degrees Celsius, joules over grams times degrees Celsius. That makes sense because that's what specific heat capacity is. So let's go ahead and try and solve a problem real quick for specific heat capacity. Alright, so let's say we have a piece of copper and we put it on a balance and its mass is 95.4 grams. It absorbs heat and increases its temperature from 25 degrees Celsius to 48.0 degrees Celsius, and it does this by absorbing 849 joules. And they want to know, well, what is the specific heat capacity of copper? Well, like I said before, the equation for specific heat capacity is Q over M times delta T. So we need to make sure we know those values. So do we know Q? Q is the amount of heat absorbed by the metal. Yes. Do we know the mass of the metal? Yes, we do. And do we know the change in temperature? Yes, from 25 to 48. But it's important that you remember that change in temperature is the final temperature minus the initial temperature. So we need to do 48.0 degrees Celsius minus 25.0 degrees Celsius, and that comes out to 23.0 degrees Celsius. So yes, we know all these values, now we just have to compute it. So we plug them in. Specific heat capacity of copper is equal to 849 joules divided by 95.4 grams divided by 23.0 degrees Celsius. We plug that in and we get 0.387, and the units are going to be joules per gram degrees Celsius. And that's an example of working out a specific heat capacity problem. Of course, you have 4 variables: specific heat capacity, heat absorbed, the mass, or the change in temperature. I could just have easily have asked you to solve for any one. I could have asked you to solve for the mass, asked you to solve for the change in temperature, or the heat, or the specific heat capacity. Alright, good luck.